Recording in progress.
All right. Welcome to the second part of the review. I will, I'll check the Zoom waiting room in a couple minutes because I know people are still logging on. But this is, I plan to have this the same format as yesterday. Take about an hour and a half, hour, 45 minutes to go through all the material, leave time for questions if there are any. How many of you are planning? You're all planning to take it sometime next week, right? Oh, you poor soul. But I will post this later today, probably by like 1 or 2 o'clock. But again, so this is just now we're into the biochemistry part, glycolysis, metabolism, all that fancy stuff. While I move on, let's start with some humor. If you feel this way in a few years, then organic chemistry did its job. This is probably how it feels right now. Just having a quick look at everything I need to know for my exams. And hopefully, this is not your organic chemistry final. Welcome to your final exam. The exam's now over. I'm afraid all you failed. Your grades have been stored on our department server and will be submitted tomorrow. Class dismissed. And I did compile, he has intermittently brought up some of his sons. So I just made a couple memes that I wanted to introduce. Well, I don't have it. And then the last one, which I think the first one's better, but this one is just kind of like eh. All right. Now let's get into it. Let me check the Zoom meeting again. Admit all. All right. So we're going to start with amines. And amines are very basic. So the problem with amines is that they're simultaneously nucleophilic and basic. NH3. And the problem in synthesizing them is that we can't do a simple SN2 reaction unless you want to go all the way to quaternary carbon. So let's say we take this and we just add a straight halo ethyl chloride. It is possible just to get the one component, but the problem is wherever this nitrogen is, or wherever this lone pair of electrons is, um, it's still basic. And actually, as we increase the substitution, at least, uh, at least with sp3 hybridized alkyl groups, it's easy to keep reacting. So it'll just react with another equivalent and do it again and again. So this is a good way to make the quaternary ammonium salts, but not so much if you want to stop at the primary, secondary, or tertiary position. It's just not very selective. The other thing you want to keep in mind is that the basicity of the lone pair of atoms on the nitrogen is influenced by resonance and hybridization, and to some extent aromaticity, which is really a application of the first two. So if you had to compare, say, this amino, I want a better example than this. If you wanted to compare pyridine, pyridine with this, which one you say is more basic? Yeah, the left one is more basic. So both of these species are aromatic, but this lone pair of electrons on the nitrogen does not contribute to aromaticity. Does not contribute to aromaticity, whereas this one does contribute to aromaticity. So this one is less, and this one is more basic. Now, since we can't get to the primary, secondary, or tertiary via a standard SN2 reaction, we have to find a couple of creative ways in order to synthesize those primary, secondary, and tertiary amines. We talked about this a little bit yesterday, how you can go from the alcohol all the way to the carboxylic acid. You can take the primary amine, oxidize it. There's really no way to do this except with a carbonyl component, but you can think of it as an oxidation because we add more nitrogen to that carbon nitrogen bond, and we're losing more electrons from this carbon. But anyway, I bring this up because it shows you a useful transformation. So the primary amine can go to the imine all the way to the the nitrile. And if you have a secondary amine, you can bring that up to the enamine. Now you can't go forward in this direction, but you can go in the backwards direction. So it is possible to take a nitrile with whatever R group attached to it, and we can simply treat that with lithium aluminum hydride, do an aqueous workup, and that readily gives us a primary amine. Now you want to be careful with this because a lot of people will miss out on this carbon. Some people will probably just go RNH2. No, that's wrong. You have to have that extra carbon in there. Always count your carbons. It makes a difference. A way to get to secondary and tertiary means, oh yeah, I should add this as well. We can't actually go all the way up to the amide. So if we have an amide, depending on what's substituted onto it, we can actually turn that into a primary, secondary, or tertiary amine, depending on if we have 0 R groups, 1 R group, or 2 R groups. So if it's 0 Rs, it makes a primary amine. If it's 1 R, it makes a secondary amine. And if it's 2 R, can you still see that in the corner? Yes, no? I'm gonna move that up. Move this up and make it a little smaller. We can take the amide, and what do you know? We can also reduce it with lithium aluminum hydride and do an aqueous workup, and that gives us the primary amine. Now, the intermediate for this, it's a little bit more complicated of a reaction mechanism, but it does go through an imine first, and then that imine gets reduced to a amine. Now, that's basically the way to get to primary amines and secondary and tertiary amines, so I'll just skip that. But one special way, which is actually near and dear to my heart for primary amines, is the Gabriel synthesis. And what happens with this is that you have this, I don't remember the name. Anyone remember the name? It's like phenolphthalein. It's a PH-TH sound. But anyway, the point here is that, well, it's not NH2, it's just NH. In a normal amide, you'd have two R groups, just straight alkyl chains. But this one, you've restricted that because now you have the two carbonyls on either side. So what you'll do here is actually just treat this with a base and a primary alkyl group. And this one only works to make primary means because it's already limited to what we can add to it. And then with this, now that we have our R group attached, we can do a deprotection with hydrazine. I think there's something else in there, but I don't remember what it is. That's going to release this and our primary amine. So yes, the Gabriel synthesis only works for primary amines because we have the two groups occupied at this and this position. So bottom line, if you want to get a primary amine, use a Gabriel synthesis or reduce the nitrile group. If you want the secondary or tertiary amine, get to the amide first and then reduce it with lithium aluminum hydride. That's pretty straightforward stuff. And don't forget the basicity, because it does depending on where it is, if it's hybridized or in resonance with something else, it delocalizes it, making it less concentrated on that nitrogen. All right, now on to chapter 23, peptides. The amide bond is very strong. Why is this? So let's just construct one really quick. So it's always going to go, whenever you see a peptide or a string of letters, the convention is it's going to go from the C terminus to the N terminus. So I'll just make a generic one, OOC minus. Wait, does it go N to C? Yes, that's what I was thinking. C, N to C terminus. N for the amino group and C for the carboxylate group. I was like, no, this is wrong. Something is not right. Have an R group. Then we have the amide bond. Nope, that's just one H actually. Then we have the other R group. Then we have the other amide. Another R group. Amide. This. Amide. Feel like that's not right. Yes, if it is just the amino group. Right. It's the C terminus. Duh. There, that's better. Now, why is the amide bond strong? It's because it's a group 4 electrophile. So here, your organic chemistry knowledge is coming into use. Since it's a very non-reactive electrophile, it keeps that whole peptide string intact. And what is the reason for that? Well, it all has to do with resonance, because this lone pair of electrons on each of those nitrogens, except for the one at the very end, is resonating into the carbonyl adding to stability in the overall complex. We want the amide bond to be strong, otherwise all of our proteins would easily degrade and we'd be in serious biological trouble. Now, the thing you have to keep in mind is you have to be able to, you do need to know all 20 amino acids. They're one-letter codes, they're three-letter codes, and you have to look at the string of little letters we and determine what the charge is at physiological pH. So the easy way to do this, which I derived myself, and no one teaches it like this, is this. So you just look at the pH and compare it to whatever the pKa value is. So if the pH is less than the pKa value, the side chain or the N or C terminus receives a proton. If the pH is equal to the pKa, you won't see this as much. It'll be half protonated and half deprotonated because that's at equilibrium. If the pH is greater than the pKa, that's more basic, then you lose, it's fully deprotonated. So it's easy to look at the amino acids, and you notice that the carboxyl groups and the amino groups all have about the same pKa. About 2 for the carboxylic acid and 9 to 10 for the amino group. The only things that make a huge difference are cysteine because it's a sulfur, tyrosine because it's a phenol, aspartic acid and glutamic acid because they're both just carboxylic acids, and lysine, which is that is just another amino group, so it's around 10. So yep, you see a 10. Arginine is that special guanine group, and histidine is that aromatic nitrogen. Do you want to see a demonstration of these rules, or should just move on? Anyway, the thing you do not ever want to forget about for determining charge, because it's not explicitly written, will be your N and C terminus. Your N is around 9 to 10, and your C terminus is around 2 to 3. At physiological pH, those will just balance each other out. So you don't have to worry about it if it's 7.4. But if it's 2 or even lower, then you have to take them into account. And here's a useful question. I know he likes to ask this. But is the why is the carboxylic acid in the amino acid more acidic than the straight up than a normal carboxylic acid? So let me draw that out really quick. This is like 2 to 3 versus this one would be like 4 to 5. Why is the amino one more acidic than the non-amino one? What's different about the two? Yeah. So what to remember about nitrogen? Nitrogen is an electrophilic compound. So nitrogen, since it's only 2 bonds away from the carboxylate, is actually withdrawing electrons through the inductive effect. That makes the proton on the carboxylate more exposed, therefore lowering the acid or increasing the acidity of the carboxylate and decreasing the pKa. That's always funny because increased acidity means a decreased pKa. But, I didn't invent math. I wonder if God invented math. Who knows? Something else to keep in mind, which we didn't go into excruciating detail about, is solid phase peptide synthesis. Now, I won't go over these individual steps, I'll just show you the general principle. Now with this, so the problem with amino groups R O H minus NH3 plus R1. Let me leave off the extra hydrogen and positive charge for now. So since this nitrogen is not part of an amine, an amide, this is very basic. So you cannot do a straight up amidation or a condensation with with any amino acids floating around because you have a nucleophilic end and you have an electrophilic end. Nucleophilic, electrophilic. So these amino acids could either combine with themselves or they could combine with each other. So like this could go here or here. Simultaneously, this could go here or here. So just with two amino acids, we already have the possibility of getting four unique products. More if you think about tri and quadrupeptides. So the strategy for solid phase peptide synthesis is the first thing you have to do is you have to attach it to a polymer. Because see what this does? This blocks off the electrophilic end of the polymer. What you also need, and this is absolutely crucial, is an FMOC or Bach protected amine group. So FMOC, whoops, I always forget to switch from highlighter to pen. So FMOC or Bach is specific for amine. It is a specific amine protecting group. And what does that do for us? Well, if we have NH and Bach, and then our amino acid, again, I'm just keeping this generic as R, this blocks the nucleophilicity because it's not just a nitrogen attached to some group, it's actually a carbamate. And that looks something like this. And I don't remember what it looks like. But the point is, it's similar to an amine, or no, an amide, where this pair of electrons will be resonating with the carbonyl oxygens in that Bach group, so it's not nucleophilic. So not nucleophilic. However, once you remove that protecting group, either with piperidine or TFA for the FMOC, now you've regenerated your nucleophilicity. And then now you have to react that with another FMOC nucleophilic blocked amide with an available electrophile in order to continue building your chain. So you just add on a protected amino, you add on protected FMOC group, take it off, add on another one, take it off, add it on, just however many you want to do, however many cycles you need to get to your peptide chain of choice. And the last step, of course, is you have to remove the FMOC group and cleave it from the polymer. And that's how you get your tri or quatra or pentapeptide. Now, they do have a machine that does this upstairs for us. Has all the 20 amino acids. You just say, I want this sequence of letters, and it synthesizes the whole thing within an hour. So, hooray. They don't teach that in the undergraduate lab, but maybe they should. Okay, this is something else he likes to put on there. So remember with the antimicrobial peptide, this applies to the alpha helix. And if you have to do this, you will get the 16 helix wheel with all the numbers labeled. But the point is not so much in that it is a helix wheel, but in where the placement of charges is of the individual amino acids. So roughly, you want to divide this in half and look at the charge of the individual amino acids. So this will just pretty much be at pH 7.4. And you want to analyze each of the amino acids one by one. You'll want to, if you get like a 17 or 18 amino acid sequence, you just go through the helix and label it A, B, C, D, E. So let's go through this one really quick. So L, lysine, that's a nonpolar one, that's 0. Lysine, 0. Methionine has a sulfur, but it's not charged at physiological pH. Lysine, 0. Methionine, 0. Isoleucine, which is basically lysine, is 0. 0, 0. Valine is also 0. Now let's look at this other side. Serine is not charged, but it is hydrophilic. 0. Q is aspartate. That's the carboxylic acid, so that is actually charged. Same with serine. That should be an OH. Minus, minus. So the whole point here is that on one side of the helical wheel, you want to have nonpolar amino acid side chains. And on the other side, you want to have hydrophilic and charged amino acids. Why do we need it to be structured in this particular way? It's because the helix wheel will wedge its way into the phospholipid bilayer of the microbe, and it will degrade the membrane. It's like imagine taking a sharp knife and just cutting yourself open, and then everything just comes eviscerating out. That's what the antimicrobial peptide does. Everything just leaks out. You can't do that with cancer cells, but you can do that with bacteria because they're little itty bitty pieces. All right. So we have discussed to some extent the structure of alpha helices and beta sheets. So key points to remember is the direction of the alpha helix. So what you're going to do, you're all right-handed, right? Or you all have a right hand, Rial? So what you're going to do is take your right hand and curl it around the bottom end of the alpha helix. And your thumb has to be pointed up. Wait, no. If it curls around this way, so like this one, it's rotating like this, and your thumb points up, that makes it a left-handed alpha helix. No, right-handed. That makes it a right-handed alpha helix. If it's the opposite way, going down like this, you have to switch your hand around and your thumb points down. In order to make that work, you have to take your left hand and curl it around. So if it curls up, it's a right-handed helix, and if it curls down with your left thumb pointing down, it's not a good thumb. It's a left-handed helix, but most of the time you will have a right-handed helix. But the whole point of the alpha helix and also the beta beta sheets is that the amide groups will line up in such a way so that the R groups point out and the amide groups point in. And the amide groups point in order to achieve hydrogen bonding. You can see that with this diagram right here. So most of the time in an alpha helix, you'll actually have nonpolar side chains And in the beta sheet, you'll have that as well. Now, because the shape is restricted, you do need a way to predict which amino acids will prefer one type of structure over the other, which is why we have our handy dandy Ramachandran plots. So this is very qualitative. You haven't had to do any advanced calculations for this, though if you talk to Dr. S, he'd be happy to take you into his lab and not pay you. Um, but here, if it's in the upper left quadrant, that prefers the beta sheet, which is just this. And if it's in the bottom left quadrant, it's going to favor the right-handed helix. And if it's here in the top right quadrant, it's going to favor the left-handed helix. Any questions about that?
Sorry, jumping back to the antimicrobial factories. I was thinking that one side had to be positively charged.
Yeah.
Charged. Vacuum.
Yeah, this is a bad diagram. Let's switch that to arginine. Charged. Yeah, it does have to be positive. I was thinking that. So it has to be mostly positively charged on the one side and completely neutral on the other side. Okay. So if you ever see a Ramachandran plot, it's probably just going to be like you're making a beta sheet, you're designing this peptide. We want to make a beta sheet. Which amino acids below would most likely help you make that beta sheet? It's not that it's not that the amino acids can never form that one particular shape. It's just it's more prone to form one shape over the other. Does that make sense? That's probably going to be the easiest question on the exam. Unless you had to generate the Ramachandran plot. Now that would be an interesting question. All right, now we get our sweet revenge with carbohydrates. So these three sugars you absolutely need to know, and the relationship between them. Because if you know the relationship between them, it's easy to memorize. We have glucose, we have mannose, and we have galactose. So glucose, so I'm just going to draw the chair conformation. Unfortunately, I can just copy. Oh, no, I'll copy it once I draw it all out. The first carbon is the anomeric carbon. There's no preference for alpha or beta. But the other carbons, here, let me label the carbons. 1, 2, 3, 4, 5, 6. The other hydroxy groups, as well as this methylene methoxy group, has all OH groups in the equatorial position. That's the most stable conformation you can have in the chair form. Now, mannose is exactly the same, except what we change is the position of the hydroxy group at the second carbon. So now, instead of being equatorial, this hydroxy group is now in the axial position. What is the relationship between, what is the stereochemical relationship between glucose and mannose? Yeah, they're epimers. They're diastereomers, more broadly speaking. But if we only change one stereocenter, change one stereocenter, it becomes an epimer. And that's a unique type of diastereomer. Ooh, that's not good. Now, at least I'm self-conscious enough that I'll rewrite the word. Dr. Price will just say, oh, well, it's poorly written. Good luck figuring it out. Now, galactose, again, is the same as glucose, except now at the fourth carbon, it's no longer equatorial, it's axial. I don't know why I just drew an X. There's no OX in there. And again, this is also an epimer of glucose. Now, what's the relationship between galactose and mannose? Are they epimers? No, because you switch two groups. So mannose and galactose are diastereomers of each other. But they are both epimers of glucose. I don't know what the carbon-3 epimer of glucose is, but we didn't learn it, so you don't need to know it. But this is something you do need to know. I think he said in class something about like open chain form to linear form. This is if you have a model kit, use the model kit. If you don't, I'll show you how to do it. And this might show up on the test, so we'll see. So this is the easiest way to convert from the open chain form to the linear form. So this, do you go over anomers at some point? Yeah, I do that in the next slide. So this you want to first convert to the cyclohexane form because it's easier to see it with the wedges and dashes. Except for this one, I'm going to relabel all my carbon atoms in oxygen, calling oxygen 1, 2, 3, 4, 5, 6. So here's our straight chain, here's our cyclohexane form. 1, 2, 3, 4, 5, 6. And you look at the orientation of the hydroxyl groups. So 2 doesn't really matter. That's our anomeric carbon. I'll go over that in the next slide. 3, that's pointing down below the chair. So that's going to get a dash. 4 is pointing up. So that's going to get a wedge. 5 is also pointing up, so that is also a wedge. 6 is pointing up, so that's a wedge with this. Now is where we convert it to the straight chain form, where we actually slice this bond. Again, I love copy and paste. Where that gets converted into our hemiacetal. So that's why the orientation with this one didn't actually matter too much. It converted into a non-stereogenic center. But now we have to work our way down the chain. So I'm going to put my, how do I want to do this? O, OH. Now we have to convert it to its linear form. And this is one reason you want to label the carbons. And this 6 should actually be over here on this carbon, not the carbon sticking out on the chain. 6, 6. This is going to look a little funky because your 1 and your 6 are right next to each other. But it makes sense if you're in the ring position. So 1, 6, 5, 4, 3, 2. So 2 doesn't have any stereocenters associated with it. Let me make this a little bit, well, let me copy this and erase those numbers. So now we just have to work our way down the chain and figure out what position our hydroxy groups obtain. 1, 2, 3, 4, 5. There is a carbon missing, but it's because it's going to be the CH2OH group, and we'll address that in just a second. So on the third carbon, so this is how I like to look at it. So you see this 3 right here, it's in this position. So if we rotate it just a little bit, we get a valley like this. But if you look right here, it's actually the opposite orientation. So in order to get this to match, we have to rotate it 180 degrees. So that's why this goes from here, a dash, into a wedge. Yes?
I thought the OH on carbon number 5 would be down. Or, oh, this isn't.
Yeah, this is I'm doing galactose. Yeah. Does this make sense, the hill versus the valley? Okay. So that was carbon 3. And if you look at carbon 4, see here, see how it points down? And this also points down like this. That does not have to rotate to get into the zigzag form. So that is also just going to, that's going to take, it's going to keep the same wedge. Now 5, so 5, you can see that this is now pointing up. But see how this one is kind of pointing down? So we have to, in order to get it to match, we have to flip it. So that goes from a wedge to a dash. And then the final one, Do we have to flip that? I don't think so. This one, this final one is in that is in this orientation right here. And this one's pointed down. Wait, do we have to rotate that? It's tricky. Yeah, we'd have to we would have to rotate it to get it into that specific position. So it's going to take the opposite orientation. Whoops. And there's our extra carbon. Now with this one, we still have to do one more step because this carbon at the very end is actually supposed to be part of the zigzag. So let me once again copy this. What we have to do is rotate this, and it helps if you put in the extra hydrogen. This is where the model kit comes in handy. I'm going to rotate it this way. So I just think of it as everything that had everything just shifts by one position. So the OH group, the CH2OH group will go from a dash to a wedge. I mean, to the straight chain. The straight chain will go to the solid wedge. And the solid wedge will go to the, oops, that should be OH. The solid wedge will go to being a dash. So just redrawing that for clarity's sake, OH, 1, 2, 3, 4, 5, 6, OH, OH, OH. There's your straight chain form of the galactose. Now, if you're not super confident in your ability to view this, to twist it in your mind, what you can do is label each of these individual centers as R or S. So like if it's all R, you can just draw out the straight chain form and put the hydroxyl or the methylene hydroxyl in the right position to get that same stereocenter. That's one way to do it. It's a little bit longer. Bring your model kit. You are still allowed to use it. Now here's where we get into a little bit of chemistry. So you notice that when we had just this, when it's in the cyclic form, this the second carbon, or really the first carbon, gets a little squiggle. Why is that? Because it could actually take on two different orientations. And for all intents and purposes, we're just going to say that these two things are in equilibrium. And it has to do with the way that the OH group is facing with respect to this this last group on this sixth carbon. So if it's pointing down like this, that's trans to the last group. That's an alpha anomer. And this is, and if we have it pointing up like this, that's cis to this last group, making it the beta anomer. Why does it have the chance of equal amounts of both enantiomers? Well, remember that even though that glucose is 90% of the time, the sugars will be in their cyclic form. Let me finish this and I'll answer your question. It's because we get this a or wait, we get an aldehyde. And remember, the aldehyde is completely flat. So there's no preference for top side or bottom side attack. That's why you get a 50-50 mixture of both. If you forget what the alpha anomer is, just if the question says, is this an alpha anomer or beta anomer, just flip a coin and you'll be right 50% of the time. Or just learn it and get it right 100% of the time. What was your question?
It was about the gene one. I was thinking that for glucose, and they have
This is galactose.
lactose. I was thinking that would have RSS and R series on this. And so I was thinking that I guess the carbon, the leftmost wedge, I was thinking that would need to be a dash, so it would have instead of staying 7 next to the rightmost.
1, 2, 3. That's S. Let me check my rotation really quick. You're right. I rotated it in the wrong direction. Should be going this way. Now it's S. Okay. And remember here that for your cyclic chain form of the sugar, this is a hemiacetal. So the hemiacetal can open and close instantaneously. But if you transform this into an acetal, so say take the same thing and just put a methyl group on there. What is that? Talked about it yesterday. An acetal is a protecting group. Protecting group. So if you have an acetal, it locks it in as the alpha or the beta anomer. And so most likely you'll probably have a long sugar polymer where you have to identify the individual subunits, whether it's glucose, mannose, or galactose, maybe fructose, because you've seen that in glycolysis. But you have to identify the type of glycosidic bond that is contained in the atom. So if we look at these three molecules, for example, let's label our carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is attached to carbon 1. Yeah, one highlighter. And this is attached to carbon 5. So this is a 1 to 5 bond. But if it's at the anomeric carbon, you have to designate it as alpha or beta. So in this one, is this an alpha or beta anomer, the left sugar? Yep, it's an alpha. It's an alpha 1,4 glycosidic bond. You know, I thought I would remember this, but I need to let some people in on the Zoom meeting. Or no, that's it. Wow, few people than yesterday. Oh well. I got 20 views on my YouTube video last night. I'm actually pretty happy about that. That's the most I ever get on any YouTube video I post. Okay, again, you want to label the carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is a 1 to 4 connection. Is it alpha or beta? Beta. And then finally, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's a 1 to 4. Is it alpha or beta? If you do have a glycosidic linkage to the other anomeric hydroxy group, then you just add alpha or beta in front of that 4 or whatever that attachment is. It's not common, but it does happen. Can't believe it's already been 53 minutes. Don't worry, there's still lots of good stuff to come. All right, now we get into lipids. So the chemistry of lipids is pretty straightforward. It's mostly dealing with hydrophobic nonpolar side chains. The thing you want to distinguish between is waxes and triglycerides. So a wax will just have the ester group in it, so with a non-fatty acid or saturated alkyl side chain on either side. Triglycerides follow the same pattern, except you've got 3 esters and 3 fatty acid side chains. So if you hydrolyze the wax, you would get I'm not being too particular about the carbon counting. You would get the carboxylic acid and the alcohol. You would get that same thing here as well, the carboxylic acid of the 3 individual carbon atoms and the glycerol. The glycerol with the 3 oxygens attached, or our 3 hydroxyl group attached, is what distinguishes a triglyceride from a wax. Now, the only thing unique, I guess, we did with the lipid part of this class was that we modified the triglyceride just a little bit. So one was a phosphatidyl ethanolamine, which all we did here is we switched out one of these waxy side chains with this phosphatidyl ethanolamine group. And what that does for us is this gives it, so in the normal triacylglyceride, everything's just nonpolar hydrophobic. But with this one, we actually have a hydrophilic charged species, which will change the structure of your lipid polymer. Phosphatidylcholine is the same thing. It's exactly like phosphatidyl ethanolamine, except now we have three methyl groups, which makes a quaternary ammonium. And then the last one was sphingomyelin. which was basically the same as phosphatidylethynolamine, but this we switch out for an amide group. And still considered a fatty acid side chain, but it's just an amide instead. The thing that changes the structure the most is definitely this polarly charged side group. And this gives us into the possibility of forming micelles. There is a blank version of this on Learning Suite if you want to annotate that as we go along. I forgot to mention that at the beginning. The other big thing we did in this hydrophobic chapter was terpene identification and synthesis. So with all terpenes, you are looking for the isoprene chain. And it really doesn't matter how you label it. You know, I wish we could, I don't remember what lecture that was when he's like, this is not a terpene, but someone pointed out and said, oh, actually, it is a terpene. You remember that? So you're all, but regardless of how you number it, you're always looking for that basic pattern. And you're looking for a multiple of 5 carbons, 5, 10, 15, 20. A full terpene actually contains a full 10 carbons. If it contains half that amount, it's sesquiquet. But I can never pronounce that word. Isn't it Latin? Meaning 1.5 or something? Sesquicentennial. That was also a funny moment. It's like, you probably haven't seen this prefix before, sesquiquenta. It's like, have you been at BYU for the last 7 months? Sesquicentennial year? Anyway, the point is you want to look at that isoprene subunit and wedge it in such a way so you can correctly identify the terpene. And the dead giveaway is if you have a branched dimethyl head group, that has to be the front end of that terpene. If you have an ethyl group coming off the ring like this, that's a giveaway that it has to be the end part of this of the isoprene. But anyway, let's identify the isoprene subunits here. So that's 1, 2, 3, 4, 5. Ooh, that's convenient. Here's our dimethyl bridgehead and our ethyl group at the very end. So yes, that is a terpene. And you can have other atoms attached to it. It's just the carbon skeleton that has to match up. Now let's go to this one, bisabolene. So here's 1, 2, 3, 4, 5. That matches up. Here's a dimethyl bridgehead over here, 1, 2, 3, 4, 5. And then right here, 1, 2, 3, 4, 5. That matches up. If you get any rearrangement of this, it is not a terpene, or at least we can't classify it as one with the isoprene subunit. This last one, that's a tricky one. Taxidiene. Let's see, 1, 2, 3, 4, 5. There's one. 1, 2, 3, 4, 5. There's another. 1, 2, 3, 4, 5. There's another. At a conjunction point, at an actual bridgehead between a point between two fused rings, that's a good place to assign your dimethyl head. Now, as far as synthesis goes, we're not going to go over synthesis. I'm not going to go over an example of synthesis, but what you want to keep in mind is this is all carbocation rearrangement chemistry. So if we take geraniol and just pop off that OPP group, you notice we get a positively charged carbocation. We can resonate that into the next bond over. So let's see. What are the different rules? We have resonance, which just puts it into the allylic position like that. You could also have rearrangement. So this probably wouldn't happen, but let's say we put the positive charge right here. Could it rearrange to get it over into this position? Yes, because we could shift a hydride over. In order to put it on that position, and now we have resonance right here. Now, in general, the syntheses that you have seen move the carbocation from a less stable to a more stable position. Hydride and methyl. And if we want to end the synthesis, so this is during the synthesis where we're moving the electrons around, moving the positive charge around, and attacking with the pair of electrons from the other alkene. That is during the synthesis. But to terminate the synthesis, wait, how do I want to say this? So beginning, does that have two ends? I don't know. Beginning, we take off OPP in order to generate our carbocation. Throughout the middle of the synthesis, we shift the carbocation charge around. To terminate it, we have to do a, what's the word? We have to deprotonate it. So say we take this molecule right here. We have the positive charge on that. In order to quell that positive charge, we have to have a base and we have to deprotonate the alpha carbon next to the carbonyl because that alleviates this pair of electrons in order to come down to the carbon-carbon bond and form a pi bond. Yeah, I did not draw that very well. You know, I'm so grateful we have tools like ChemDraw. It's certainly slower, but it does look a lot neater when publishing the paper. I don't know what they used to have back then for publishing. Probably something archetypal and dinosaur, primordial. All right, DNA. So I didn't go a lot into DNA either, but you do need to know the basic structures and functions of DNA. So DNA and RNA both contain of 4 unique bases. So purines are when you have the 2 rings, and that's adenine and guanine. And this you do need to know the structures of adenine, guanine, cytosine, thymine, and uracil. It's annoying, but it is what it is. I memorized it once and I forgot it. Whereas the pyrimidines just have the 1 nitrogenous ring. And what makes DNA actually work is that we pair a purine. We always We always pair a purine containing base with a pyrimidine containing base. So A will always bond to T and make two hydrogen bonds, and G will always bond to C in order to make 3 hydrogen bonds. So the tricky part of this is that you can't line these up directly. You have to flip one over in order to get the hydrogens and lone pairs to line up. And I don't know if you noticed this before, but these bases have a unique property. Do you know what it is? What did we do? What do we do with rings, with benzene rings? They're all aromatic. So this is one reason that DNA is a very stable molecule is because it has a very stable, it has an aromatic ring, either two for the purine, 1 for the pyrimidine. Evidence for creation over evolutionaryism, whatever. Those guys are doofuses. Wolves evolved into whales. That's what my biology teacher would say. Wolves evolved into whales. It's like, okay, I guess whatever works for you. All right. Now, you do have to distinguish. So the base without any, there is nucleoside and nucleotide. Both of them have the sugar attached. If there's no sugar attached, it's just a nitrogenous base. There's no special "ide" name for that base. Now, this is how I remember the difference between a nucleoside and a nucleotide. S, remember your alphabet, Q, R, S, T, U, V. S comes before T in the alphabet. A nucleotide has no phosphate group. A nucleoside, no phosphate group. Nucleotide, yes, phosphate. The reason I say S before T, you have the nucleoside before you have the nucleotide. No phosphate before the phosphate. Does that make sense? Yes.
Good question from that. We have to know which group.
Highlight it. Identify what base pair it is. You don't have to actually identify what the major or the minor groove is, but it might highlight a specific section and say, what is this? What is this? What are these bases? And the way you tell that is all based off the hydrogen bond. So if you have a thiamine A pair, that's actually really easy. The first, if you ever see a question like that, did you have that on your midterm? Anyway, the first thing you want to look for is the methyl group, because the methyl group is unique to thiamine. If you have the methyl group on the left side, it's going to be a TA. If it's on the TA, if it's on the right side, it's AT. For if you don't have the methyl group, it's going to be a CG or GC bond. And the way you're going to figure that out is just look at the order of the atoms. So here you'll have a carbon, oxygen, hydrogen, nitrogen, carbon, or you'll have the carbon, nitrogen, oxygen, carbon. You won't see that middle one because it's way wedged in there. Okay, any questions about that? Okay. All right, now we get into our favorite thing, which is metabolism. Glycolysis, citric acid cycle, and fatty acid oxidation. So I'm not going to go over the electron pushing mechanisms for this. I'm just going to point out the transformations, because if you know the transformations, it is fairly easy to figure out how to push the electrons. And this is all just applied organic chemistry, all on steroids, because it all happens all at once. And I'm sorry, but you do need to know all the names of the intermediates and the names of the enzymes, as well as the cofactors, lipoamide and tyrosine pyrophosphate. No, it's TPP. I don't remember what the full name is. TPP, and whether or not ATP, ADP, NAD plus, or FAD are involved. Sorry, but it's rough. Anyway, but the whole point of all the metabolism we have is to generate energy. Funny enough, this is how we stay alive. So we generate energy in the form of ATP. Now, throughout from glycolysis to the citric acid cycle to even beta oxidation, we are generating electron carriers, NADH and FADH2. These will move on to the electron transport chain, which is where we'll actually generate the bulk of our ATP. So I won't point out those specific steps right now, but basically NADH and FADH2 are carrying electrons in the form of the hydride ion. and that'll get onto the electron transport chain. Did someone have a question, or just raising his or her hand? Okay, so that's the place we're going with all metabolism. Now let's get into glycolysis. So this, you do want to keep careful track of where all of the carbons in your intermediates are going. I actually got this, I took this out from my biochemistry textbook. Whenever I upload things to Learning Suite, it says, if you're uploading, wait, what does it say? It says something like, if you're uploading copyrighted material, do you have the permission? Yes. Do I have the permission? No, I just pretend like I do. But no one's going to see it besides you. And it's probably just going to get buried in the archives of Learning Suite anyway. You know, the scriptures talk about like the great burning and cleansing of the earth. I wonder if something is going to similar happens to Learning Suite. Some administrator is just going to delete all files and this it goes away completely. Or why don't we just delete Learning Suite? Anyway, so this is in the Hayworth projection. Sorry about that, but this still shows the useful transformations. So notice we have the carbons labeled here 1 through 6. So in the first step, going from glucose to glucose 6-phosphate, we're using a kinase. So this is just transporting a phosphate group. And this first step is irreversible. Because this right here, ATP, is a phosphoanhydride, which is a group 1 electrophile. Remember back way in chapter 14 or 13. And now this is a phosphoester, a group 2 electrophile. So because we're changing the reactivity of those of the electrophile, this first step is considered irreversible, and that's really what starts it off. And of course, we use hexokinase as our enzyme. If we're ever moving a phosphate group and only moving a phosphate group, it's a kinase. It might be a different type of kinase, but it's still a kinase. Now, in the second step, this is where we do some isomerization, where we transform this. Notice how this is the hemiacetal. Well, that ring is going to open up and actually change the position of where the carbonyl group is. And if you want to go over a mechanism, we can do that at the very end. But for right now, I'm just pointing out the transformations. But what it's going to do is it's going to change the position of the carbonyl group. So now that the hemiacetal is on carbon 2 hemiacetal, instead of on the first one, carbon 1 hemiacetal. That's pretty easy. That's just phosphohexose isomerase. The next step is where we get, the next step is just another kinase where we add on an ATP to this first, or a phosphate group onto this carbon. Now this is where it gets a little tricky because now we're going to do an aldolase reaction, or really it's a reverse aldol. See, it's chemistry on steroids. Now you can't actually make steroids. It did ruin a lot of careers. Thank you, Lance Armstrong. So anyway, the reason this gets a little tricky is because now we're splitting the atom in half. We're going from 1 6-carbon species to 2 3-carbon species. Let's see, did I put this on the next slide? Oops, I forgot. I left off dihydroxyacetone phosphate. Anyway, let's work with what, let me look that up really quick because I do not want to get that wrong. Wrong spot. Let me just look it up really quick. Don't go snooping around on my unopened tabs. Hydroxy acetone phosphate. There we go. Oh, well, that's useful. Comes from the same textbook. Come on, copy. Well, that was fortunate. Where do I want to put this? I'll just put it over here. Anyway, so glyceraldehyde. Oh, wait, not doing the transformation yet. So we have to keep track of what carbons from glucose ended up in glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So how do we do that? Well, notice how we have the carbons labeled here, 1, 2, 3, 4, 5, and 6. Well, the left side becomes glyceraldehyde 3-phosphate, and you know that the phosphate was on carbon 6 originally. So it just goes 6, 5, 4. And throughout the whole rest of the process, it'll always be 6, 5, 4, 6, 5, 4, 6, 5, 4. Now the other side is a dihydroxyacetone phosphate. And that, you notice that the phosphate was on carbon 1. So this will always be, where is that? 1, nope. 1, 2, 3. And then since dihydroxyacetone phosphate gets transformed into glyceraldehyde 3-phosphate, because glyceraldehyde 3-phosphate is what undergoes the rest of glycolysis, your numbering will look like this: 1, 2, 3, 1, 2, 3, 1, 2, 3, and so forth. Now it looks a little odd because they're in opposite ascending and descending orders, but this is easy to remember if you remember that 1 and 6 were originally connected in the glucose ring. So that's why they're opposite. Make sense so far? So yeah, keep them in. I think he does like to put that type of question on there. Like which carbon is this? First, second, third, fourth, fifth, or sixth? Anyway, after we do a tautomerization or an isomerization with triose phosphate isomerase of dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. Now this is the payoff phase where we're going to get back our ATP. So this is the first step. So you see here, we oxidize the molecule, and this is where I'm going to point out the individual transformations now. Notice how this is an aldehyde and it's going to a phosphoester. So these ones, or is that a phosphoanhydride? Actually, I think it's a phosphoanhydride. So this one, notice that this step is reversible because this is going from a group 1 electrophile to a group 1 electrophile. So it doesn't actually take much energy to do it. But it's not just a simple, what do I want to say? It's not a simple oxidation, although you can think of it as an oxidation. It's a dehydrogenase because you notice you take off this hydrogen, and that hydrogen is going to end up getting transferred to over here in the NAD plus to become NADH. So this will eventually go to the electron transport chain. So we do that, and then here is also another irreversible step because we're going from a group 1 to a group 1. Actually, no. Yeah. Oh, yes. No, this has it drawn wrong. This arrow, nope. This second arrow should not be here. This is going from a group 1 electrophile to a group 4 electrophile because that's a carboxylate. So this step right here is irreversible. And really, this is where we pay off all the ATP, or we recuperate the ATP we use in the first few steps. Because we had to use one in step 1 and one in step 3, but in step 7, since this is happening twice with 3 carbon species, we're now at 0 ATP generation. We'll get back up there, but we need to do a couple other things first. Okay, 3-phosphoglycerate. Did I clip that one too? Now this one, yeah. Wait a second. 7. Yeah, that's the same thing. So now the 3-phosphoglycerate actually gets transformed into 2-phosphoglycerate. And that's a weird one. It's a mutase. We're changing the position from carbon 3 to it's not actually carbon 3. From the third carbon, wait, how do I number this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It gets transferred from the first carbon in the chain to the second carbon in the chain. And that's a complicated mechanism. You do not need to know that. Most chemists don't know how it works. At least that's what I tell myself. Now this one right here, we're going from 2-phosphoglycerate to phosphoenolpyruvate. This is just a reverse aldol reaction. We're actually generating here an enolate equivalent. Except this, instead of a hydrogen, we have a phosphate group on there instead. And the final step where we ultimately get where we get to pyruvate, this is where we finally pay off the irreversible. Thinking too many things at once. This is where we get the net 2 ATP. And notice how this is this one right here is just another, well, no, this is not, I would call, what is it? It's tautomerization. Because see here, this was the enol form, and now it's the keto form. So one reason that this step is irreversible is because we're going from the less stable enol to the more stable keto. Remember that from yesterday? Keto form is more favored. And it's also favored because it kicks off the phosphate group. And pyruvate is already a very charged molecule, and phosphate is also charged, so they're going to repel each other. Any questions about glycolysis? Is this good so far? Good pace, good tone. I didn't bring my thing, but there's more humor at the end. All right. So we're not done with metabolism. We're done with glycolysis, but before we go into the citric acid cycle, we actually have to lose one carbon. Pyruvate is a 3-carbon species versus acetyl-CoA is a 1-carbon species. So the obvious transformation you would see here is this what is it? It's a carboxylate. But we cannot do the carboxylation at that position. Why? Because we don't have anywhere stable for the electrons to go. If we had that carbonyl in this position, then we generate this as our leaving group, and it would be stable because of resonance. So this is where it turns out we need a little bit of help from the cofactors. And this thiamine pyrophosphate and lipoamide are directly involved in order to create a stable place for that lone pair of electrons to go. So this I also grabbed from my biochemistry textbook. This is nice because it illustrates very well how it doesn't show electron pushing. Most biologists do not even think in terms of electron pushing or electrons or atoms or anything. Most biologists say, oh, chemistry, whoosh, out the window. Some of them will be like, what's a carbon-carbon bond? But, such is life. So if you've taken organic chemistry and you understand electron pushing, you're already a way better biologist than most doctors because you actually understand the biology. Because what is biology? Applied chemistry. Okay, so here's what's happening. First, pyruvate attaches to the thiamine pyrophosphate. What this does is it will attach at this point right here. And since it's attached to this nitrogen and this sulfur, where's the other one? It's pyruvate. OH. Once this comes off as CO2, this pair of electrons now has somewhere stable to go because it can resonate into the ring with that nitrogen group. That's the whole point of thiamine pyrophosphate. We have resonance within this heterocyclic ring. Is it? Oh, it's also aromatic. How convenient. Aromaticity all over the place. Anyway, that allows us to get rid of one carbon, but now we have to now we're going to use our lipoamide, and notice it has this long fatty acid chain. This actually gives it some good flexibility. So it can spin around. So the disulfur bridge is the oxidized form. And here we reduce it in order to pick up those two carbons from that did come from pyruvate. And now look at this. This whole group right here is what? What type of functional group is it? Thioester, yes. So we make a thioester before we make the thioester of acetyl-CoA. So the lipoamide acts as a transition point where we can get to into the right location in order to add on CoA enzyme. So because we're going from a thioester to a thioester, there's no energy change. And once we kick that off, then we just oxidize it again back to the disulfur bridge, and we actually get off an FAD and an FADH2. This is oxidizing agent. The FAD oxidizes from the disulfide to the disulfur bridge. All right. And that's one payoff we get. FADH2, transitioning from glycolysis to the citric acid cycle. Oh, the citric acid cycle is a doozy. We'll just go over it really quickly, and I'll point out the chemistry that goes along. So the first thing that happens is a Claisen condensation, where the methyl group of acetyl-CoA, gets converted into methylene in citrate. So see here, this is a methyl group, and here this is a methylene group. That's from my highlight, which proves that I own the book, but I do not own the copyright. So this, notice we have 1, 2, 3, whoops, why did I skip 3? 3, 4, 5, 6 carbons. We're going to lose a couple of carbons throughout in order to produce carbon dioxide. Now the second step, using aconitase, is now switching where that position goes. So look right here. That is just an alcohol Now it's an alkene. And the reason we do that is so when we rehydrate it, we put the alcohol on a different carbon. So we're shifting this alcohol from this carbon to this carbon right here. And the reason that is important is because we need to perform oxidative decarboxylation. So this will take so the alcohol and isocitrate will get oxidized to a ketone. And that ketone notice how it's in the beta position of beta alpha that's in the beta position of the carboxylate. So this one doesn't need any special cofactor like pyruvate to acetyl-CoA. This one can just happen readily because the pair of electrons already has somewhere to go. All right. So that's where we lose the first carbon. And this next one, alpha ketone glutarate dehydrogenase complex, this is where we convert this end from a carboxylate into a thioester. And this one is exactly like the pyruvate dehydrogenase. So this one you do actually need, because the ketone in that position is not in the right position to do the decarboxylation, that one actually does need the special cofactors in order to do that decarboxylation. So that's where we've lost our two carbons. And from this point on, we only have a 4-carbon species. And that just gets only thing that happens is that we shuttle electrons around at this point. We're not doing anything else with the straight carbon chain. So let's see. Succinyl-CoA gets transformed into, we phosphorylate it and then lose CoAsh, and that gives us a succinate. Now here's the second payoff step. Here we'll take FAD, transform it into FADH2 in order to reduce it. To oxidize it. What's the transformation here? Beforehand we had 2 methylene carbons. Now we have 2 vinyl carbons, form a fumarate. And why do we need that? Well, we need that double bond in order to perform a hydration. So that'll add on to this carbon right here. And the final transformation is an oxidation, just a secondary alcohol to a ketone. Now, I think I've seen this question before. Why do we need this specific oxaloacetate? It's because this one, combining the acetyl-CoA and the oxaloacetate, that's a Claisen reaction. That is, in fact, the first step of glycolysis, Claisen condensation. It puts the keto group in the exact right position. We need to start the cycle all over again. Okay, I'm getting tired of metabolism. Just one more thing to do and a couple of reactions from chapter 28. So fatty acid metabolism is considerably much simpler and the transformations are much easier to see. So you see the first thing we do here, I'm sorry I'm not going over all the fine points. You do have to know these, however. We're transforming this straight chain alkane. We're oxidizing it to the double bond. And why do we need that? So we can perform hydration with water. Remember that reaction from 351? Where you add an alcohol across an alkene, we'll see 351 never goes away. It just shows up, it just rears its ugly head in lowly places. Now, the reason we put on this alcohol in this position is so now we could oxidize it to a ketone. Oxidation was all in 352, right? I think so. So this is chapter 14 coming back to haunt you. Anyway, the reason, so again, you see this is a very common pattern in all the metabolism steps. We make an alkene, we add a OH group to it, we oxidize that OH group to a ketone, and now we can just do a retroclason reaction. Where we add CoA, bring up the electrons, bring them down, and kick off the whoops, wrong thing. It'll kick off this end. And where does acetyl-CoA go? Yep, it goes into the citric acid cycle. So citric acid cycle is really where everything comes together. And why is that useful? Because we're producing more NADH and FADH2, which will go on to the electron transport chain. Okay, I'm done with metabolism. So we talked a little bit about some new chemistry. I really think the important part here is less knowing the mechanism, like the oxidative addition and the migratory insertion and the reductive elimination, and more about being able to identify the connections to get to the main product. So we have Heck, Suzuki, and olefin metathesis. So Heck, what you're going to look for is your aryl or vinyl halide. Most common ones are bromine and iodine. And you're going to look for a vanillic hydrogen. Now you have to be a little, and you're going to look for your palladium catalyst. Without the catalyst, this will not happen, which is why the person who discovered it won a Nobel Prize. Let's see. So here, let's identify the products. So we have the aryl halide right here, and we have two vanillic hydrogens right there. I think there is a case to be made for selectivity, but right now we're just going to say that they're equally reactive. So this bromine, or rather this carbon, can either attach at this position or this position. Let me copy this so I don't have to do it again. So if it attaches at the end, we make this product. If it attaches in the middle, we make this product. And the important thing about this is that stereochemistry is retained. So if the alkene here was a Z, then it will still be a Z over here with respect to whatever's attached to it. Now this one, let's again do the same thing. So we have our, oh, this actually won't work. Why? It's not an aryl halide. Not aryl or vinyl halide. So you have to have those, you have to have these two specific groups in order to make the reaction work. Otherwise, it just doesn't do anything. Now, the Suzuki reaction is basically more of the same thing, except what you're connecting is an aryl halide or a vinyl halide with a boronic acid or a boronic ester. And of course, you have to have your palladium catalyst. So the boron is specific to the Suzuki reaction mechanism. So if we try to predict the products of this one, we have the halide, we have the boron. Uh-oh, what's wrong? Yeah, it's not the right type of halide. So this one will lead to no reaction. What about this last one? Do we have an aryl halide here? Yep, right there. And we have this boronic acid. So we'll end up combining this end and this end of the molecule. And since it's the boronic acid, we only get one product, unlike the heck, where we can get a mixture of products. And see, the stereochemistry is retained. And the last one we'll go over is olefin metathesis. So the thing you have to, so what this is it's combining two alkenes in a ring in order to close the ring and produce ethylene gas. You're always going to lose a net of 2 carbons in this mechanism. If you do this with the linear form, if you do this with linear molecules like this, you're going to get a combination of things. You just have to line them up carefully and figure it out. I don't think he'll make you do that kind of thing. Intermolecular is way more common and way more selective. But the thing you have to know about olefin metathesis is you have to have the ruthenium catalyst, Ru. If you don't have Ru, it's going to become Fu, and you will get this question wrong. So this one, you just identify the alkenes. So it'll join, well, actually, so this carbon, these 2 carbons will end up leaving as ethylene. And it's these 2 carbons right here that end up combining. So what you'll get is, whoops, I'm on a marker. Now people are dropping like flies. I mean, it is basically the end of. You'll get that as your product, plus ethylene. I'm not going to redraw. I just don't want to. And same thing here. So these carbons, and these carbons as well, will end up leaving as ethylene. And this carbon and these carbons will combine as well as these. With this one, there's a mixture. There's possibility of a mixture of products. I'm just going to stick to what I drew already. So 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2. 1, 2, 3, 4, 5. 1, 2. 1, 2, 3. 1, 2, 3. So we'll make that. Let's see. Where's the branching point? 1, 2, 3, 4, 5. Yeah, it's coming off of this carbon right here. And this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Happens between 1 and 5. So that's the product we make right there. So identify the connection points, eliminate ethylene, and the double bond will form between whatever these end carbons are. Okay. Right. Now as one last piece of humor. So remember that in the beginning, he said, what is it? Where's my vape? Well, I can't synthesize a vape for you, but you can actually get your own methamphetamine. What you need to do, and you don't need a prescription for this, you can go to the pharmacy and buy a Sudafed or pseudoepinephrine. You can take that into the chemistry laboratory and reduce that hydroxyl group to a hydrogen. It's actually it's a couple of steps, but it's not terribly difficult. So if you say here, yo, where's my vape? You're just gonna go to the pharmacy and make it directly. All right. All right, that is the end.